So I want to show a graph, again, horizontal axis. This is a graph you've seen before. Horizontal axis is the time in thousands of years before the present. I'm going to show you one cycle of that repeating roughly 100,000 year periodicity ice age cycle. So we've seen this graph before. It shows the deviation in temperature from the present, which is read as 0 on the horizontal axis, the deviation in degrees Celsius. You'll remember there was a number I wanted you to walk away from this course with, and that number was the rough difference between the present and sort of the middle era of an ice age, and that was on the order of 6 or 8 degrees Celsius. You can quibble about the numbers. So that sort of sets the scale for the temperature variation. And you saw that characteristic pattern that repeated again over about 500,000 years of a fairly steep rise into these interglacial periods of moderate temperatures, the kind of temperatures the Earth is experiencing now, followed by a long decline into this cool ice age period. And there's a lot of fluctuations within that ice age. It's not a smooth decline. It's not a steady cold temperature. A lot of fluctuations, and then something triggers this rapid warming. We've seen that before, and that's what this picture shows. Now, what if we put on top of that same graph the carbon dioxide concentration as measured from the same ice cores? Instead of working here with oxygen isotope ratios or hydrogen isotope ratios, we're working instead with actual analysis of the air trapped in these ancient air bubbles, the fossil air that's in there, and we can measure the carbon dioxide concentration. And the most remarkable thing about the two graphs, the upper line being the carbon dioxide, whose scale is at the right, the lower one being the temperature, whose scale is at the left. The most remarkable thing is they seem to track almost perfectly together. They have exactly the same shape. They have that 100,000 year periodicity between highs in temperature and highs in carbon dioxide. They have that long decline into lower temperatures and lower carbon dioxide. So there is a remarkable correlation between the Earth's average temperature, at least to the extent that these Arctic and Antarctic ice cores reflect Earth's average temperature, and we think they do. There is a remarkable correlation between carbon dioxide concentration and global temperature. And with a lot of other data sets going back a lot farther in time, we have very good reason to believe that correlation holds to a very good extent throughout much of Earth's history, if not all of it. So there is a very strong and obvious correlation between temperature and carbon dioxide concentration. Now, before you read too much into this, it is not the case here that somehow the Earth's carbon dioxide content increased, the atmosphere's carbon dioxide content increased, and the temperature went up with it, and then the carbon dioxide went down, and the temperature went down with it. It's not as simple as that. As I suggested when I first showed you the temperature graph a few lectures back, there's a subtle cause and effect thing going on here that involves orbital changes in the parameters associated with the Earth's orbit. Some of those changes include the eccentricity of the orbit. How elliptical is it? Earth's orbit is not a perfect circle. It's slightly elliptical. Earth is about 3% closer to the sun at its closest approach than it is at its most distant point. And if I were to ask you, think a second, when is it closest to the sun? You might want to pause your DVD a second or pause your tape and listen. Think about that. Well, I'll answer it for you. The Earth happens to be closest to the sun in January. And that's when the northern hemisphere has its winter, and that effect makes the winter-summer difference less substantial than it would be. If that were to change, and it changes partly with changes in the eccentricity, the ellipticity of the orbit, it changes partly with changes in the tilt of the Earth's axis at 23 degrees. That change occurs on about a 41,000 year cycle. The orbital eccentricity changes on about 100,000 and a 400,000 year cycle. There's also a change associated with the so-called precession of the equinoxes, the fact that the North Pole doesn't always point in the same direction, but on a cycle of about 25,000 years precesses around. I showed you why in my video series, Physics in Your Life. It's like a big top precessing. It takes 25,000 years. So the North Star is now in the direction of the Earth's polar axis, and 12,500 years from now it won't be, and 25,000 years from now it will be again. All those effects conspire to make subtle changes in the climate. For example, at some point, the closest point to the sun will be in June. And when that happens, the summer-winter difference will be exaggerated. And you might say, well, doesn't that just reverse in the southern hemisphere? Well, it doesn't, because the southern hemisphere has a lot less land, a lot more water, and so the effects are different. So there are all these subtle effects. So what we believe happens to trigger this simultaneous change in carbon dioxide and temperature is there are these orbital effects. They're small, but they're regular, they're periodic, they're big effects on or small effects on the Earth's orbit, but they're big effects on the climate because they trigger a small change in temperature. And then we believe other changes occur. For example, the oceans get a little warmer. That means some of the carbon dioxide that's dissolved in the oceans comes out. That goes into the atmosphere. That makes more greenhouse warming. That makes more carbon dioxide come out of the atmospheres or the soils. And there are a host of other changes like this called positive feedback effects that we believe leapfrog and bring about that fairly rapid rise in both temperature and carbon dioxide, till we reach these interglacial temperature maxima like we're in right now. And then gradually, as the orbital parameters change a little bit, those conditions go away. And then gradually, again, working in step, the carbon dioxide goes down and the temperature goes down, and that drives the carbon dioxide down, and they go down step by step. So it isn't quite that, yes, carbon dioxide increases and so does temperature. In the long history of the Earth, they go up and down together. And the important point is they're strongly correlated. So that's evidence that this greenhouse effect is really happening, that the carbon dioxide content of the atmosphere helps determine what the temperature of the atmosphere is. Never mind the fact that the carbon dioxide and the temperature kind of worked on each other to get up and down in that 100,000-year cycle we've been talking about. This relationship, we're pretty sure, holds a lot further back. For example, during the age of the dinosaurs, which was on the order of 100 million years ago, 60 million years ago, 200 million years ago, that kind of time, we know that warm climate organisms existed in what are now tropical regions. CO2 levels then were maybe 1,000 parts per million, maybe about 4 times what they were before the start of the industrial era, and the temperatures were far higher than anything the planet is looking at now. Over the very longest term in the history of the Earth, it's not so much orbital processes like I've described here for the ice ages, but geological processes, volcanism, volcanoes putting gases into the atmosphere, and plate tectonics, the movement of the continents to different places on the Earth, and the weathering of rocks which can release carbon into the atmosphere or take carbon out of the atmosphere. Those are believed to be the main drivers of climate over the time scales of hundreds of millions of years and billions of years. And we believe and have good evidence that the carbon dioxide content of the atmosphere was high during times when the temperature was also high. So one of our big pieces of evidence that supports the theory of the greenhouse effect is this very tight correlation between carbon dioxide and temperature over many, many time scales in the history of the Earth's atmosphere and climate. But still, it'd be nice to do an experiment. Well, we can't, as I argued at the beginning of this lecture, but nature has done an experiment for us, and it's provided us with our neighbor planets, Venus and Mars. Now, you recall I kind of outlined a simple calculation in which I said the Earth receives energy at the rate of 240 watts per square meter approximately, and it must therefore get rid of energy at the rate of 240 watts per square meter. And we know the rate at which a hot thing gets rid of energy by infrared radiation, and that depends on its temperature, and that sets us up an equation that we can solve for temperature. Now, we can do the same for the other planets. And this gets a little bit subtle, but if you assume those other planets are basically just chunks of rock with no atmosphere, and you do the same calculation, well, Venus is closer to the sun, so you'd expect it to be warmer. It turns out that because of that energy loss going as temperature to the 4th, you don't have to change the temperature very much to compensate for Venus's proximity to the sun. So if you calculate what Venus's temperature ought to be, given that very simple calculation I sort of did for Earth, or outlined for you for Earth a few lectures ago, you get that Venus ought to be at about 55 degrees Celsius. Now, that doesn't sound real hot. It's hotter than it is here on Earth. It would not be comfortable for us. It's nowhere near the boiling point of water, on the other hand, which is 100 degrees Celsius. It's different from Earth, but not dramatically different. You do the same calculation for Mars, you get something on the order of about minus 50 degrees Celsius. Now, that's cold, but it's not so cold it would freeze the atmosphere or something like Pluto, whose atmosphere is frozen on the rocks of the planet's surface. No, it's cold, but it's not that cold, and that's because Mars is about 50% further from the sun than the Earth is. So that's why Venus is a bit closer, about 2/3 as far out as Earth is, because that would explain these relatively minor differences in the temperatures of these 3 planets. However, as I say, nature has provided us with an experiment in the form of the planets Venus, Earth, and Mars. And Earth, of course, if you do that calculation, we already did that basically, and we found that Earth ought to be at about minus 18 degrees Celsius, 0 degrees Fahrenheit. So here's the numbers again. Minus 50 degrees Celsius for Mars, minus 18 degrees Celsius for Earth, and getting closer to the sun, about 55 degrees Celsius for Venus. what are the actual surface temperatures? Well, we know those well. We have spacecraft roving around the surface of Mars. I've showed you in the first lecture how we calculate the average surface temperature for the Earth. We've had spacecraft go through the Venetian atmosphere. We know pretty well the composition of these planets, of their atmospheres, and so on. And we know what the temperatures are, the surface temperatures are on these planets. So if you look at Venus, Earth, and Mars, and look at the calculated temperatures, 55 degrees Celsius for Venus, minus 18 degrees Celsius for Earth, minus 50 degrees Celsius for Mars, and you ask, what's the actual temperature on these planets? There's a dramatically different answer for each one.